All right, today it says we're doing chapter or section 6.5. The actual lesson, the title of section 6.5 is Trapezoids and Kites. But if you look at your lesson plan, I decided to split it into two. Is that all right with you? Because today's shorter, but since you got out of chapel early, today's probably the same length as what it normally is. But that's all right. We're just going to do trapezoids today, and that's it. All right. So let's draw a trapezoid. You remember what a trapezoid is? It's a shape. Yeah, it is a shape. That's true. It's not wrong. But specifically, besides being a shape, what's the most general thing about this that you know? It's got four sides. Well, just about this right here, right now. Okay, what's shown to you right now, I haven't marked anything. I haven't really, well, I guess I kind of did, but let's say I didn't say it was a trapezoid. Okay, what if I just drew that thing right there? What's really the only thing you can say about this besides it being a shape? It's four sides, which means it's a what? Give me a name. It's a quadrilateral, okay? That's all I know right now, okay? Now, how do I make it a trapezoid? What would I have to say about, I'll use the letters that I used in my notes. This is probably in the book, same letters, I guess. And then I, all right? So in order for this to be a trapezoid, by the definition of a trapezoid, what would I have to show here in order to make this a trapezoid? Are parallel. Very good. KJ and HI are parallel. So with that information right there, that's the only thing I know about it, okay? With that information right there, what can I say about this thing? It's a what? It's a trapezoid, okay? Because a trapezoid has exactly one pair of opposite parallel sides, okay? So one pair of sides are parallel. So that means these two are what? Not parallel. Agreed? All right. We also talked about a little bit more of a specific type of trapezoid when we talked about trapezoid in the first place. Do you remember what that was? It's isosceles. Very good. Okay, it's an isosceles trapezoid. So what makes this an isosceles trapezoid? I haven't really marked it, so you don't really know. But what could I say about this to make it an isosceles trapezoid? Yeah, the two legs right here are equal to each other, congruent to each other. Okay, these are the bases. Remember, the parallel sides are the bases, and the other two sides are the legs. Right? So, what's true about this thing? This is a what? I just said it. Isosceles trapezoid. So that was what? 2 lessons ago? Is that what it was? Something like that. Again, sorry about my voice. I'm still fighting this thing. I have a feeling it's going to be like this all week. All right, so right now there's been nothing new. Okay, there's nothing new about this. We've learned this stuff already, but here's the new thing. They give you a theorem. So this is new. It says the base angles. Now that's not new. We talked about which angles are the base angles. So we've talked about that before. That's not new. But we're going to say something specific about these base angles. Okay, so the base angles of an isosceles trapezoid, I'll just put trap. Is that all right? What do you think might be true about them? By the way, which ones are the base angles? Which ones are the base angles? You can look in your notes. We drew them. The top and bottom. So this one and this one are base angles. Which one? Give me letters. I got letters here. Give me letters. K and J. Right. K and J would be considered base angles. And what else? H and I would be base angles. Okay? Because look, this is to this base, right? That connects one side or one leg to this base. This connects the other leg to the same base. Agreed? All right, so it's the same base right here. So H and I, this theorem says that the base angles of an isosceles trapezoid are equal, or we'll say congruent, okay? They're equal to each other. So H and I would be equal to each other, so let's write that down. So angle H is going to be congruent or equal to angle what? I. And what's the other thing that's equal to each other? Angle K and angle J. All right. So that's our theorem. That's our first theorem. We got another one for a trapezoid, but that's our first one. It's pretty simple, isn't it? Yeah. Now, what do you know about K and H? They're not equal to each other, right? Because that's an acute angle. That's obtuse. They're obviously, just by looking at it, they're not equal to each other. But what do you think might be true about them? Not think, but you know for a fact, and you can tell me why. Something about K and H. What's true about K and H? You got parallel lines, so think back when you had parallel lines. And you have a transversal, don't you? They're supplementary. Okay, is that what you said, Angela? Yeah, they're supplementary. I just can't hear you very well. So these are supplementary to each other. All right. So it's not really part of the theorem. We just know it is. We know from way back in another chapter, because when you have two parallel lines cut by a transversal, these are consecutive interior angles, aren't they? All right. So they must be what? Supplementary. So it's not a new theorem. It's nothing new that we learned about a trapezoid. It's just something that we learned a long time ago that we can apply to this. So that can be very helpful. So they may ask you, like, this is 60 degrees, and they ask you to find the rest of the angles. So if they tell you this is 60 degrees, what's the easiest one to find?
The one next.
Give me a letter. I got letters here. Don't say the one next to it, the one above it. Yeah, angle I. So if this is 60 degrees, tell me something about angle I. That's 60 degrees, right? Why? Because we have a theorem that says what? The base angles of an isosceles trapezoid are congruent to each other, equal to each other, okay? So that's the easiest. So those two are 60. This one's not much effort to figure out, but what's angle K equal to now? And so that makes angle K what? 120, that's right. Because they're supplementary, right? You're the one that told me they're supplementary, right? So these are supplementary. So I go 180 minus 60, which is 120. So if that's 120, tell me something about this one. That's 120 as well. Okay? Now, you know what they're going to eventually do. They're not just going to put numbers for the angles. What are they going to put in here? Yeah, like equations, right? Put x in there, right? Then you got to set stuff equal to each other. Or you do what? You add things up and set it equal to 180. Solve for x, plug it back in, right? It's the same old, isn't it? We've been doing this. I don't know if we did that in chapter 1. We probably did a little bit of that in chapter 1. But after that, it seems like every chapter. I think we skipped 2, didn't we? So chapter 3, chapter 4, chapter 5, that's the kind of stuff we've been doing. We just do it with different shapes, all right? We just haven't done it with a trapezoid before. Everybody good with that? All right. So let's do this. Let me read it first. Now, right now, I told you that this was a what? It was given that this was a what? Isosceles what? Trapezoid, okay? So if it's an isosceles trapezoid, then what do you know about it? Well, you know the opposite sides are equal, but you also know that the base angles are equal to each other. You with me on that? So what if I give you a trapezoid? I should have just copied the other one, but that's okay. So what if I give you a trapezoid and I tell you that it's a trapezoid, all right? I do not tell you that it's an isosceles trapezoid, okay? All I'm telling you, it's given that it's a trapezoid, okay? So what do you know about this thing just knowing that it's a trapezoid? You know that the opposite, or it's got exactly one pair of what? Opposite parallel sides, okay? So these two sides would be parallel to each other. I know that from the definition of a trapezoid. Everybody with me? So this theorem says this. This is kind of lengthy. I don't know. I'll just kind of shorten it up a little bit. So here's what we know. We're given that it's a trapezoid. And again, let's put some letters in here. Is that the same letters? Yeah, same letters I used before. I and H. Okay. And so we know it's a trapezoid. And I know that angle H is equal to angle I. Okay, that's what I know. I'm given. Okay, it's given this. So angle H is equal or congruent. I'm not going to be real picky on that. Angle I. Okay. What's your gut instinct? If these two angles are equal to each other, what do you think? What kind of trapezoid is this?
Isosceles?
It's an isosceles trapezoid. Do you see the difference on the first one and this one? We changed the if-then stuff, all right? So if the base angles are equal, then it's an isosceles trapezoid. So I'm just going to shorten it like this. If the base angles are equal, then it's a what? It's an isosceles trapezoid. Very good. Okay. What did the first theorem basically say? The first theorem said if what? If it was a, what did we start off knowing? Right, we started off knowing it was an isosceles trapezoid, right? So I'll just put that. I'll shorten everything. All right, so if it's an isosceles trapezoid, then what do we know if it's an isosceles trapezoid? What else do we know? We know that the base angles are equal. Do you see the difference? All right, so this theorem right here says they tell you it's a trapezoid, all right? And they tell you that the base angles are equal. So what do you know then about KH and JI? They're equal to each other, exactly right, because that would make an isosceles trapezoid, right? So if it's a trapezoid, just a basic trapezoid, but you know that the base angles are equal to each other, then what do you know about that trapezoid specifically? You know that it's a what? An isosceles trapezoid. Okay? See the difference? It's kind of subtle, but really not. I mean, we didn't really talk about that in here, and in the past, I've spent a lot of time in geometry talking about this kind of thing, but these are called if-then statements. If-then statements. I think on chapter 2, I think we skipped chapter 2. Not that it's not important, but I only have so many days to teach you guys, and there's no way you can finish a book. There's just no way. If I taught something every single day, didn't even have any test or quizzes, maybe I could get through the book, all right? But with all the days off we have and all the times we have to review for a test and take the test and do the corrections and do all that kind of stuff, there's just really not enough time, not enough days in the school year to finish the whole entire book. It's really never been my goal. So listen, shh. Let's just listen to me talk. So that's why I skip a few things here and there, all right? Not because it's not important, but anyway, the if-then statements, here's just something. So if you see this later on, you're like, okay, I remember he talked about that very, very briefly. Maybe you'll never remember it. But we use this. We use P and Q, all right? If P, then Q. The arrow means then, all right? So if a certain thing is true, then a certain thing is true. So what is the P in this one right here? What's the if part? Yeah, if the base angles are equal, okay? I should say of a trapezoid, okay? If the base angles are equal, if the base angles of a trapezoid are equal to each other, then what's true? So what is this? What letter is this? That's the Q. So what did we do with this one, though? The Q was it's an isosceles trapezoid, right? So what did we do here? So this is the what? The Q, and then this is the P, all right? There's whole courses on this. It's on logic and logic statements and all this kind of thing. There's whole chapters in geometry books about this. And like I said, in college, there's whole entire courses on this, a whole class just on this PQ stuff. So I'm just barely scratching the surface a little bit here. All right, so I'm just introducing it to you. So if I have if P then Q, and I also have if Q then P, this is called the converse of the statement. This is our initial statement. This is the converse, where we just switch the P and the Q. And we've done that quite often. I haven't talked about the P and the Q thing, but we've switched the if and the then, all right? Not every statement can you switch the if and then, all right? But a lot of times you can, and we call this the converse of the statement. We also have a thing where we say if it's not. So if not P, and that little squiggle means not, all right? If not P, then not Q. I think that's called the inverse of the statement. It's been a while since I've taught this. My goodness, it's probably been 15 years since I've taught this stuff at least. And then you have another thing called if not Q, then not P. That's called the contrapositive of the statement, all right? Which is kind of crazy. What's kind of interesting is the statement itself and the contrapositive are always going to be true statements, okay? Just because you switch the if and the then doesn't always mean it's going to be a true statement depending on what you're dealing with. Anyway, I just thought I'd throw that in there. It just popped in my head. You may possibly see this stuff at some point somewhere. I don't know where. Usually it's in geometry. So there it is. Don't worry about it. It's not going to be on a quiz, not going to be on a test, not going to be on a homework. But I just thought I'd throw that out there. So if anybody talks to you, oh, what do you do in geometry? Somebody else says, oh, I'm doing these logic statements, if P then Q. I'm like, oh, yeah, my teacher talked about that. All right. So there you go. All right. Enough of that. So let's do one more. And then we'll do an example. And I think, no, we got to do another theorem after this example. All right. So let's draw another trapezoid. I'm trying to make it isosceles because that's what we're dealing with right now. Because there's really not a whole lot to know about an ordinary everyday trapezoid. You know that the opposite sides are parallel to each other, and that's about it. All right. You know the consecutive angles are always going to be supplementary, but there's a little bit more to know about an isosceles trapezoid. So check this out. What am I drawing right here from one corner to another? What do I call that thing? It's not parallel to anything. Diagonal. It's a diagonal, right? So I'm going to draw a diagonal like this. Now, what's your gut instinct about these diagonals? If it's an isosceles trapezoid, I should say that. So let's do this. Okay, parallel, equal. So that's an isosceles trapezoid right there, isn't it? So I got the diagonals drawn. Again, what's your gut instinct about those two diagonals? No, they don't bisect the angles. Congruent to each other, yes. And you are right. That is a correct gut instinct. How do we know that? Well, because we could prove it, or we're not going to. Again, if I tried to prove every single theorem in front of you, it would take forever. We'd never finish. Okay, so, but it is a theorem, and it says, the theorem says, if it's an isosceles trapezoid, so if it's an isosceles trapezoid, then the diagonals, whoops, what did we say? What's true about the diagonals? The diagonals are what? Congruent or equal. Equal, congruent, you can say either one. It doesn't matter. Okay, so if it's an isosceles trapezoid, which it is, the diagonals are going to be equal to each other. So what could I say? Like what line segments? Let's name the line segments. What would they be that are equal to each other? All right, Ki is one, and then JH is the other one. All right, so you know that that's true. Now, we don't know that it's not necessarily bisected. It's not bisecting these angles or anything like that, okay? But we do know that those diagonals are equal to each other. Make sense? It's not too hard, is it? No, it's just stuff that, again, my guess is if you just looked at that, you'd probably guess that Ki and JH were equal to each other, wouldn't you? But it is true, all right? So that would be a good guess. Let's do an example. Throw some numbers in here, and let's see. When are we out of here? 10:30? Is that our time? I always forget on Wednesdays. 10:30, yes. All right, so yeah, we got 20 minutes, so I got time. So let's draw. I think I'm drawing an isosceles trapezoid. I didn't write that in my notes, but I think it is. We're going to call this one ABCD. And we're going to draw some diagonals. And then we're going to put some stuff in here. On this one, I'm not even one of the things. They put some X's in here, okay? But most of them, they just tell you what some angles are. They tell you that angle. I'll tell you what, I'll put the angles in a different color. They say that angle ABC is 125. So this whole big angle right there, I'm just going to write it out here. Is that all right? Everybody understand that? So that yellow one, that big yellow one, is 125. And then AC, line segment AC, I'll just tell you what, I'm going to write it right here. AC is 7x, all right? And then it says BD is 4x plus 12. I think that's, then they might give you some other stuff too, don't they? Yeah. Yeah, I think they tell you this is 30. I don't have my book open. Who's got their book open on this example? This is example 2 on the 6.5. Is that everything they give you? They put an E in the middle, right? And that's all they give you, right? 125, 30, and then they tell you the lengths of those diagonals, correct? All right, yeah, it looks like that's what they give you. So let's go back to white. It's a little easier to read with all the writing. So they ask you a whole bunch of things, 6 different things. They ask you to find angle BAD. They ask you to find angle ADC. ADC. They ask you to find ABD. ABD. All right, angle ABD, sorry. On part D, ACD. It's like alphabet soup, isn't it? So many letters. E is AED. And then F is AC. All right. So all angles except for the very end, they ask for a line segment. Let's go different colors for all of these. Okay, BAD, where's that? BAD, that's this whole big thing right there. Well, that should be easy without any work at all. What's angle? See that blue one right there? What's that angle equal to? This is an isosceles trapezoid, by the way. Okay, it's given that it's an isosceles trapezoid. All right, so you have to know that first of all. So it is. What is it? 125. Exactly right, because the base angles are equal. Correct. So if that's 125, that's 125. So that's pretty easy. I don't know. Do I have enough colors to do a different color for each one of these? We'll see. Let's do B. ADC. ADC. That's this whole big thing right there. So how do we find that? The whole big green one. Yeah, that's right. Okay, this is 125 right here, isn't it? Remember what's true about these? These are consecutive interior angles. So what do we know about these? They are supplementary. It's also supplementary to that too, right? Because they're opposite, or because they're equal to each other. All right, they're base angles. All right, so it's 180 minus 125. What's that? 55. So that's ADC, 55. That's good. All right, ABD. ABD, that's this little one right here. That little red one right there. How do you know it's 30? Good, I like it. Parallel lines. Remember, it's a trapezoid, right? So I got parallel lines cut by transversal. Now, go a step further. Why? Why is this 30? Because they're what? You got it. They're alternate interior angles. Very good. All right, so we learned stuff way back then, and we're using it again. All right, and I think I even said that back then, didn't I? I said this is really important because you're going to use it later on, and here we are later on, and we're using it. Okay, so ABD is 30 degrees. ACD. Let's change colors. Let's go to this orangey color. ACD. ACD. That's this little guy right here. How do I find ACD? What do you think is true about that? Say that.
Isn't it also
It is 30 degrees. Okay. Why is it 30 degrees though?
because it's because it's
I'm trying to think myself. Okay. It is. It's true. I'm trying to give a good reason for it though. Um, yeah, that's 125.
yeah.
Right, the whole thing. Right, okay, that's good. So that's 25. All right, same thing here, right? Because if this whole thing is 125, then this is also going to be what? 25. And and there you go. You got 125 minus, no, you got 55 minus 25 is 30. Very good. Okay? See that? I mean, you could kind of look at them and say, oh, it looks like so if these two are equal to each other, those two angles are equal to each other, that means these two sides are equal to each other. Like from E to C, right? And E to D. Remember, if we have a triangle with two equal angles, the opposite sides are equal as well. Yeah. Okay, good. I mean, it kind of makes sense that would be 30, but it's good to be able to go through the whole thing and figure out why exactly it's
Wait,
30. So
no,
that's
you
good.
put that for
Did I do the wrong one?
yeah. You put that for AD.
Oh, this one, sorry. Yep. So that one's 30 degrees. All right, good. Different color. What color haven't I used? It's pink. AED. Where's AED? AED. That's that one right there.
I think that's 25.
Well, let's do this. I know two angles of this triangle, right? That's 30 and 30, which is what? 60. So what's this angle right here? That's 120. So now what's this angle? Forms a straight line. So how do I find that? 60. Exactly right. You see that? See, I got this one adds up to 180, correct? So this one and this one is 60. Take it away from 180, and that's 120. This forms a straight line, right, which is 180 degrees. AED. If this is 60? Yeah, we haven't figured out this one, though, did we?
No, it's 125. Oh,
Wait a minute. Is this 25, though? We didn't establish that this was 25. No, it's not. Yeah, but look. This right here, see, this whole thing is 125, right? And so this is 30. So what's this one right here? No, you're looking at the wrong angle. You got to look at the whole big angle. Two parallel lines cut by transversal. You're looking at this whole big angle right there. That's 125 because that's 125, right? The blue one is 125. If this is 30, then this one right here is going to be 30, just like it is down here. So this would be 95 right here. Yeah, but no, this is not, but this angle right here that I wrote, the 95, that is not two lines cut by transversal. Look, that line and this line are not parallel. I mean, that's a transversal, but these two lines are not parallel. So you can't use that, right? But you can do the same idea right here, right? We knew that was 30, so we did some work and we figured out that was 30. Do the same thing up here, right? And then See, and then that would be 30, and that would be 95. Now these add up to 180.
So how does it work for the other one?
Because they were parallel lines. Because AB and DC were parallel lines cut by a transversal. So this is 30 and that's 30.
So with
But
AC
this one, look, you're looking at this side, AD and BC, cut by this transversal. But these are not parallel. AD and BC are not parallel to each other. You only have one set of parallel lines because it's a trapezoid. Okay? So I see what you're thinking, but those two lines are not parallel. That's the key.
DC are parallel.
I know, but that, look, AB has nothing to do with this angle right here.
All right.
Okay?
Back on there real quick.
Now, let's finish this up. So what did we do already? AED, did we do AED? Yeah, that's this one. What did I say it was? AED 60 degrees. Because I got one more thing I got to go through, and I only got like 8 minutes now. All right, so let's go back to yellow since I wrote all that stuff in yellow. So let's find AC. AC is this diagonal right here. Well, what do they tell you? They tell you AC is 7x. Problem is, I don't know what x is. But what can I do? They give me AC, they give me BD. What's true about the diagonals of this thing? They're equal to each other. So what am I going to do here? Set them equal, right? So this is easy. So 4x plus 12. Subtract 4x, I get 3x. Divide by 3, x is 4. Now, that's not what they ask for, though. They ask for AC, so what do? Plug a 4 into that. 7 times 4 is 28, so that's 28. Okay? I'll keep it up here, but let's do the next one. Because we got to get through this. Because remember, today we're only getting through half the lesson anyway, so I want to make sure at least we get through half of it. Now, I'm going to draw another trapezoid, but this trapezoid purposely is not isosceles. Okay? What I'm going to do is this. I'm going to find the midpoint of this. Let's see, I got to do this. I'm going to find the midpoint of this one, and then I'm going to find the midpoint of this one, which is right there, and I'm going to connect them. Okay? We have a name for this, and I think we've used this name before. I think. I don't know. I teach so many of these classes, I can't remember what I said from one class to the other. I think we've talked about this before. Mid-segment, it's called. Have we done a mid-segment before? Yeah, but we did a mid-segment of a triangle, though, didn't we? Okay? Remember what's true about the mid-segment of a triangle is parallel to the third side, right? So remember, I also said that a trapezoid's kind of like a triangle, kind of, right? It's just a triangle that they cut like the top part off, right? They cut it parallel to the base, all right? So a lot of things that are true about a triangle are kind of the same in a trapezoid, and this is one of them. We'll call this M, and we'll call this N, all right? So I'm not going to write, just because of time, I'm not going to write down the theorem, but I'll read it off to you. It's called the trapezoid mid-segment theorem. So I'll write that part down. The trapezoid mid-segment theorem. Basically, it says two things, all right? I'll put a 1 and a 2. And I'm just going to use these letters to describe what's happening here, okay? Remember, it's a trapezoid, so you know this and this automatically are parallel, right? Because it's a trapezoid. Again, gut instinct. What do you think is true about MN compared to the two bases? MN, the mid-segment. That's the mid-segment, okay? The mid-segment is MN. Say it? Yeah, it looks parallel, doesn't it? Doesn't it look parallel to the other two bases? And it absolutely is. So if I make a mid-segment, it's parallel to both bases, all right? I'll call this one base 1, and I'll call this one base 2, all right? So MN is parallel to what? AB, and it's also parallel to DC. So that's the first thing that we know about it. And that's kind of one of those gut instinct ones where you're like, yeah, it sure looks like it should be parallel, right? Would you agree? Because if it didn't connect at the midpoints, it'd be up here, and that would be kind of slanted. Everybody see that? But if it's right in the middle, sure, it definitely looks parallel. And that is true. That's what the theorem says. The second one, though, is something that may not be a gut instinct thing, but I will talk about it. Let's call this, see how I call this base 1 and base 2? Let's call this M for mid-segment. We'll call it mid-segment. Put an M1 there just so you don't confuse it with that M. Is that all right? There's also something true about the length. There's a relationship between the length of the mid-segment and the lengths of the two bases. Again, it's something that you may not look at it, and it's not a gut instinct kind of thing. But I'll tell you what it is. M1 is equal to, watch this, the two bases added up divided by 2. So it's kind of like the average, isn't it? All right, so if I ask you to find the average two numbers, what would you do? You'd add up the two numbers, divide by 2. Agree? So let's say that was 3 and that was 7. All right? So let's say AB was 3 and DC was 7. How would you find the length of the mid-segment? Add them up, which is 10, divide by 2, which is 5. And that's the length of that, all right, every single time. But you have to connect the midpoints. It has to be the mid-segment, all right? So if you commit, if I could speak. If you, what word was I trying to say? Connect, that's what I'm trying to say. If you connect the two midpoints to each other, you've got the mid-segment, and the length, the distance, is going to be half of the sum of the two bases. All right, that's what that says right there. Okay? Pretty easy, isn't it? I got 2 or 3 minutes, so let's do one example, and we will actually be finished. This is a long lesson, isn't it? Because I've only done half of the lesson. So let's do this. It can be upside down. You don't always have to have the, I've been drawing these trapezoids the same way all the time. But yeah, the bottom doesn't have to be the longest side. But let's do this. Let's say this, and we're gonna draw a mid-segment. Let's see if I can do this before the bell rings. There's a midpoint. Try to be as accurate as I can here. It's around right there. Okay, if I connect from here to here, that's pretty good. All right, so there we go. I don't care about the letters. Let's say this is 4x plus 2. Let's say this is 2x, and let's say this is 10. And I want to find the lengths of the other two bases. I already know the mid-segment, don't I? Okay, so how would I find the lengths? So I have to solve for x, agreed? Do I just set them equal to each other? Is 4x plus 2 equal to 2x? No, there's no way. All right, that one's way longer than that, agreed? All right, so we don't do that, but we do our little mid-segment formula. So what is it? It's the mid-segment, which we know now is 10, is equal to what? What do I do? Add up the two bases, so that's the one base, add it to the second base, and do what to it? Divide it by 2. So that algebra is a little bit more involved than what we've been doing. Usually you just set a couple things equal to each other, or you add things equal to each other, set them equal to 180. This is a little bit more involved, but it makes sense, doesn't it? The mid-segment is equal to the sum of the bases divided by 2. So I just stuck all that stuff in here. How do I solve for x? Let's get rid of the 2. How can I get rid of the 2? Multiply by 2. Multiply that by 2. So that gives me 20. Let's add some like terms while we're at it. What's that going to give me? How about 6x plus 2? Because I'm adding like terms. Okay, 4x plus 2x. Do what? Subtract a 2. That's 18. 6x. What's x? It's 3. Now you know what to do with that, don't you? So x is, what did I say, 3? Yep. So put it into here. 4 times 3 is 12 plus 2 is 14. So that's 14. Put the 3 in for that. It's what? 6. Let's just check to see if it really works. All right. So we got our answers. So how do I know if that's the mid-segment? What do I do with these two? Add them up. 14 and 6 is 20. Divided by 2 is what? It does work, doesn't it? All right. So that's kind of cool, isn't it? Yeah. So that was a little different. Setting this up. Where did we set it up? Right here. Setting this up right here was just a little bit different than we're used to, but it should make sense. All we're doing is just sticking stuff into the formula, right? That midpoint or that mid-segment formula, that I wrote down right here. Put the 10 here, put the x's up here, divide by 2, then you just do your math. All right, we good? All right, I think, did I give you assignment? Yeah, it's 1 through 12, correct? Yep. So that should be all trapezoid stuff if I did it right. All right, so you're going to do 1 through 12. The next section, the next part of this section is about kites. All right, so we're going to kind of do the same thing. We're going to get a little bit more involved with kites. So you're doing 1 through 12, and it's section, what is it, 6-5? Is that what I said it was? And we'll call it A. All right.